Now we've talked about finding the area, and we found, let's say we want the area of that region. Simple problem, hopefully. I want this area. What's the setup? Integral from, let's call this 1, let's call this 7, 1 to 7 of f of x dx. Now, I want to point this out. This is important. Stop. Okay. What is it we're doing in theory by taking the integral? Going back. Finding the area under the curve, that's fine, but what? Yes. In theory, though, what does each one of these pieces mean, and what are we accomplishing by doing it? Remember, f of x represented the height, dx represented the width, and then the integral sign represented the sum of all these rectangles added up. You get what I'm saying here? Okay? And we are taking how many rectangles? An infinite set of rectangles to get this accomplished, right? So this is when the width of the rectangle is dx, and the height is whatever f of x is. What happens, though, if I take this same curve? Now, it gets complicated in this particular case, but what happens if I slice it into rectangles this way instead? You should, in theory, get the same answer, right? Because you're looking for the area, right? Okay, but today is discovering that relationship and how they're related, because one of these will be more beneficial than the other depending on the situation that we're talking about, okay? In a way, you're going to be dealing with the y values, yes. Good idea. But I want you to try this, okay? So there's a lot of words here, but I'm going to give you a problem here, and I want you to solve it, okay? So what's the area of the region bounded by rad x and y equals 2 and the x-axis? So figure that out first. Do that first. Okay? Did I say x-axis? Okay, y-axis, sorry. So graph it with your brain on your paper, not with your calculator. Rad x and y equals 2. So you should have, if you're looking at your notes, yes, some of you are on there, what'd you get as an answer? 8/3. Let's go through that, and then I'll have you discuss. If I'm going to graph this, radical x looks like this, right? And then we have y equals 2 does something like this. So we have to figure out where they intersect. And now we are looking for the region that's bounded by y equals 2, the curve, and the y-axis. So we're looking for this piece, right? So in this whole thing, does the upper function change? No, the upper function is always the line, right? So it's going to be the integral of the upper function. What's the upper function? 2 minus the lower function, rad x, and then dx. Now, your lower bound is easy enough. What's your lower bound? 0. How do you find your upper bound? You set them equal because you're looking for the point of intersection. So you're going to say rad x equals 2, and then square it, so x equals 4. So that's my upper bound. So analytically, antiderivative, what's the antiderivative? 2x. This one's going to be x to the 3/2, and in front will be 2/3. And then evaluate it from 0 to 4. So that's going to be 2 times 4 minus 2/3 times 4 to the 3/2. And then the zeros are all zeros. So this is 8 minus what? 8, 16/3. So that's 24/3 minus 16/3. You okay with that? Okay. Now, discuss, like what I just showed you up here with these graphs gives you an idea. I want you to try and figure out a different approach to solving this problem instead of slicing it this way. Okay, find somebody and talk for a minute about this concept. All right, since you guys are absolutely wasting time talking about nonsense, why don't I just give you the answer. Come on. How are we slicing this? We're slicing it this way, right? Because dx is the width of the rectangle. Well, how wide is the rectangle really? Infinitely thin, right? So I'm just going to draw a line that represents the rectangle. Okay, that's this way. If I were to regraph this, though, it's going to be the same graph. I'm going to slice it this way. So now, how wide is each rectangle? dy. So that means everything inside of here must be in terms of y. These limits are what? These are x values because this goes from 0 to 4. But these values should be y values, right? Okay? So if you take your head and you turn it 90 degrees, right? What you end up having actually is only one curve. You get what I'm saying? Watch. How would I take my function? What's my function? Y equals rad x. How would I take that and make it in terms of y instead of in terms of x? So how do I get x by itself essentially? Square it. So you get y squared equals x. So actually x equals y squared. So what I'm going to do, I'm going to turn everything on its head. Normally this is the x-axis, right? This is the y-axis. I'm going to make this the x-axis and this the y-axis. Right? Well, in this graph, what is your input value? Your y value, right? Like if I'm creating a table? No, it's not necessarily rotation. You'll see in a second. What? Right. Okay, you're not, turn your head like this just to get an idea, but this is still when x is positive and y is positive, right? So we still want positive. Think of it this way. When you first learned how to graph this rad x, you plugged in x values to see y values, right? Well, let's do the same thing here, but instead of plugging in x values, let's plug in y values. What's this going to look like?
Like a parabola.
It's going to be a parabola, right? If this is the x-axis, this is the y-axis. So let's plug in y equals 0. What's the value? 0. When y equals 1, x is 1. Okay. What I was thinking there. When y is 2, then x is 4. So we're going to end up with a parabola. You guys okay with that? Now, again, we are looking for this region. Well, this is 2 units tall. So instead of 2 units tall, it's going to be 2 units wide. So that's 2. You guys get me here? Okay. This side? Because we're only concerned about what's in this first quadrant. If we were to graph the other side here, that would be like graphing down here, which we could do, and we'll talk about why that's important in a minute. How tall is this? That's 4 because this was 4, right? You guys okay with that? I'm just showing you the comparison between the two graphs. Instead of x, y, we're talking about y, x. So how would I set this up to find this area here? It's going to be the integral from 0 to 2 of y squared dy. You'll see in a minute. Okay? I know you like the other way now, but look at this versus this. This is way easier. Right? You'll see why it's important in a little while. Because basically what we did is instead of dealing with everything in terms of x's, what are these limits? They're x values. Instead of the function being in terms of x, we put it in y values. Instead of dx, we do dy. So how wide is it? It's dy. How big is this length? This length is the distance from the y-axis out. So what kind of value is this point? What kind of value is it? That's an x value. Right? You went over, didn't you? That's an x value. What kind of value is this? It's a y value. This is a y value. Okay? So these will produce the same answer. Watch. Calculate it. What do you get? 1/3 y cubed from 0 to 2. So you got 1/3, 2 cubed, and then the rest is 0, so you get 8/3. What's that? Good. We're going to talk about it, and I'll give you an example of why this is important in a second. First of all, we did use everything in both cases. The 2 minus rad x, the 2 became a what? The 2 became a limit, right? Instead of being a function, part of the integrand, it became the limit, or part of the limit. Okay? The rad x kind of was dealt with the y squared. Do you guys agree that rad x and y squared are the same thing? Rad x and x squared are inverse functions, aren't they? Okay. And then the 4, yes, we're integrating from 0 to 4 here, but the 4 here represents the height here. And we don't, when we're setting up the integral, we don't care about the height so much. Okay. So let's ignore this for a second and look at this graph. We're looking at, instead of the limits being this way, we're looking at the limits this way, right? You guys okay with that? And if we look at the limits this way, we have to have, instead of y equals, we have to have it say x equals. And that's it. It's the same setup otherwise. Why would this be beneficial in some cases? Because you go, I can calculate this, even though the integrand is more complicated, I can still calculate this without doing this. Okay? In a sense, you're not replacing the x and the y, though. You're just solving for x and working with that y value as your variable now instead of your function. Okay? You'll see it as we go along. One case, I'll show you what this might mean for you. Let's say I wanted, let's say I wanted that area. I wanted the area bounded by the y-axis and the curve. Is this curve a function? No. So we can't just take the integral. Watch what happens. If I take the integral, first of all, that's like a circle. So let's make up a number here. Let's call this 3. What's the equation of that circle? Y equals?
Y squared. Same thing, but you have to check the y. Y squared. And I'll put 1/2.
Okay. No. You guys got. We're not talking about area here. Oh, I get what you're saying. Okay. What's the equation of the circle? Not what's the area of the circle. Okay. We can calculate the area of the circle by saying 1/2 pi r squared. So we can evaluate that. But this is not the equation of this circle. This is the equation of this part of the half circle, right? Okay? So maybe I don't have an equation here for this. And besides, if I were to set up an integral from what to what? 0 to 3, right? What would I be finding the area of? Just this part, because we're talking about the function. So then you could argue that you're going to multiply by 2, right? But that's fine for a circle. What happens if the curve, let's see. What if you have something that looks, something like this? And you're finding the area of this piece. You see, you can't evaluate this unless you turn your head and you see this function looks something like this. Do you get what I'm saying? Yeah, when you get to that problem, you just turn your head 90 degrees. Yeah. Okay. So this is not a function. We can't say this function is y equals f of x because it's not a function. What we can say, though, is that this is f of y. Right? And so now let's call this A and call this B. The answer to the area of this region is the integral from a to b. What kind of values are a and b? Y values. The integrand is in terms of y, and then our dy at the end. You don't have to switch the graph to see it. You just have to get everything in terms of y. Okay? So integration with respect to y. Step one. Solve for x. So instead of having y by itself, you need x by itself. Okay? Step 2. Write the integral in terms of y. So that means you're going to have an integral something y dy instead of something x dx. Okay? And then you evaluate the same way you have before. You just got to set up the equation and go. Yeah, it's that easy. Well, yeah, you just graph it, and then we'll talk about what to do from there. All right, let's see what we got here. You should have at least graphed it. That's e to the x, right? What is the x-intercept? Listen to my words. What is the x-intercept? There is no x-intercept. In fact, you have a what? What's it called? What's it called? Horizontal asymptote at x equals, or y equals 0. Because, what's a horizontal asymptote? It's when the limit as the function approaches, which way? Negative infinity approaches 0. Okay, and then you have y equals e, so that's the constant. Our first method, our normal method, to find that area would be to do what? Find the points of intersection, yes, but ultimately, you're going to take what? The integral of the upper curve minus lower curve. Okay, so what is the point of intersection? 1, okay. So previous method, okay. So we find the intersection, so we're going to say e to the x equals e. In other words, x equals 1. So our limits are from what to what? 0 to 1. Of the upper curve, which is e, minus the lower curve, which is e to the x dx. And we can evaluate that. That's fine. What's the antiderivative of e?
It's like I know it's like xe because e is a number. So
E is a number, so e is like 4. What's the antiderivative of 4? 4x. So ex. What's the antiderivative of negative e to the x? Negative e to the x. So we got e to the ex minus e to the x from 0 to 1. So we're going to get e minus 0 minus 1, which is 1. Okay? That's the old method. What's the first thing you got to do in the new method? Okay, how's it old? We just learned it yesterday. See, I'm copying her joke again. Okay, new method. What's the first thing we do? Get x by itself. Solve for x. So how are we going to get y equals e to the x to say x equals something? X equals natural log of y, right? Now everything's in terms of x. Do I have, if I look in terms of, everything's in terms of y now. So if I look in terms of y, that means this represents the height in a sense. Is there an upper function here? If I'm looking this way? No, there's only one curve. What is e now? E is a limit. Or it's the upper bound. So what are we going to say? The integral from, we want y values. So from 1 to e of natural log of y dy. The integral from 1 to e of the natural log of y dy. Are you guys okay with that? Okay, we got it in terms of y, we got the limits. Now, you guys would all be tempted to say the integral of natural log of y dy is 1 over y. That's the derivative of natural log of y. What is the antiderivative of natural log of y? I honestly don't remember. I don't. Let's see. Remember, I showed you this the other day. I didn't show it to you, but I just gave you the equation. The integral of u dv is equal to uv minus the integral of v du. I'm not saying you have to know this, but if you're curious, pay attention and see if you can follow it. Okay? I've got to identify u and dv here. So I'm going to say u is equal to, what can I take the derivative of? Because I need to take the derivative of u. ln y. Therefore, dv is equal to dy. So do you agree that this is, if I say it this way, this is u dv? Okay. So now I've got to find du. What's du? 1 over y. Actually, 1 over y dy, because I got du over dy. And then what is v going to be? If dv is dy, then v is y. The antiderivative. Right? So now, let's plug it in. What's uv? uv is u times v, so it's y times natural log of y minus the integral of what's v? Y times what's du? 1 over y dy. Watch what happens. They cancel. So here we've got y natural log of y minus the integral of dy, 1 dy, right? Now I can evaluate that. So we got y natural log of y minus y. Now this was a definite integral, right? So I'm not asking you to understand this. I'm just evaluated from 1 to e, right?
So you won't,
This is not going to be on the test. I'm just showing you how I'm just showing you that you can analytically solve the second part. So what would this be? This would be e natural log of e minus e, right? Minus 1 natural log of 1 minus 1. Well, e, what's natural log of e? 1, so that just goes away. Minus e, right? And then what's natural log of 1? 0, so this is just going to be negative 1. So that's 0 plus 1, so it's 1. No, it's a good example in terms of how to get it in terms of y and write the equation. I agree, you can't analytically solve the second part, but look at, and that's why in the lesson I put a question mark. Okay, but look at the setup. This setup versus this setup. This setup is cleaner because there's not a sum or a difference. It's just natural log of y. Now, I don't expect you to know the antiderivative of natural log of y, but the ones that I do expect you to know will be on there. Okay? Go ahead.
You just gotta know s or the integral of v dv equals that whole thing, and then you'll be
Don't worry about this. Worry about that. What's the first step if you're looking at it in terms, when you're looking at it sideways?
solve for x.
Solve for x, reevaluate everything in terms of y, right? That's it. Okay? And the reason you would want that is maybe you don't have a function, you have just an equation of something but no function. Okay? So, yeah, calculator there if you're going to do that. Okay? Let's go for a problem you can do. What is the area bounded by x equals y squared minus 1 and negative x plus 1? So you should have gotten that as a graph, right? Now, when you guys looked at this and you solved for y to get the graph, a lot of you had this, right? Now, is there a region that's enclosed by those two curves? In this one, the area bounded by this and this, there is no region. So that means the curve has to wrap around. This line's going to keep going. So this curve has to wrap around somewhere so that you do get an enclosed region. Now, why is it that I do include the bottom part here? Right, you got a plus or minus because this is not a function. It says x equals y squared. It doesn't say y equals rad x. If it said y equals rad x, then you're only looking at part of it. Does that make sense? Now, the second point I want to make is the first method that I gave you a couple days ago will not work on this. And the reason you can see why is, let's say in this region here. Let's say on the left side of the y-axis. What's the upper curve? The blue, right?
Yeah.
What's the lower curve?
Red.
It's
Also.
The blue. If we're trying to use the old method, it's going to be the upper curve minus the lower curve, right? So it's going to end up being 0, which we know is not true. Actually, we could evaluate it as the upper curve minus the lower curve if we designate this as the negative part of it. But that's just making it more complicated than it needs to be. So let's look at it in terms of y. So what's the first step I have to do?
So for x.
Okay, that one's already solved for x. This one's not, so let's go ahead and do that.
X equals negative y.
X equals what?
Negative y.
Or y minus 1? 1 minus, yes, I was meant to say y, 1 minus y. Okay, so since the blue line is not a function, it's easier to integrate in terms of y. You could, in some cases, continue doing it the old way, but not in all cases. Okay? So we're going to solve for x, and the first one's already done. The second one is going to be x equals y, 1 minus y. Now, if I look sideways, which graph represents the upper function?
The parabola.
Because if we're looking this way, let's say at this value, what's the value of the blue? Is it positive or negative? It's negative because it's on the left of the y-axis. What's the value of the red? Positive. So which one's greater? The red. So what's the equation? The integral. Okay, we got to get. The next step is we got to get the points of intersection, right? Okay. So let's get the points of intersection. Set them equal. So we're going to set x equals y squared minus 1 equal to x equals 1 minus y. And then we got a quadratic. So our zeros are what? Negative 2 and 1. And notice these are y values, right? They're not x values. So now what's my equation?
The integral from negative.
Negative 2, the integral from negative 2 to 1 of,
The upper function.
what's the upper?
1
1 minus
minus
y,
in parentheses
and then minus the lower function, which is y squared minus 1. And again, make sure you got parentheses, especially around that second thing, because you have a sum. And then dy. Okay. Simplify that a little bit, I guess. What's the antiderivative of negative y squared? Negative 1/3 y cubed minus 1/2 y squared plus 2y. And then evaluate it from negative 2 to 1. And I'm not going to dwell on that. That's just arithmetic. Here's maybe more indications. Maybe more indications that you're going to want to look at it in terms of y instead of terms of x. If I have, let's look at the tangent. Or that's not, yeah, that's something like tangent. Something like that. I don't know. Maybe it's negative tangent. I don't know. Yes. Because we're looking at it this way now, right? So which curve is greater in this direction? Okay, so how do you know which curve is greater? The top one, because we're looking at it this way, right? How do you know which curve is greater? Now we're looking at it this way. So which has a greater value? It's not up and down, it's side to side. So which has a greater x value? That one. So looking at it this way, which one has the greater values? the line has the greater values, right? Okay. All right. Depending on which part I'm looking for, let's say I wanted this region. What would be an easier equation to work with in terms of y or in terms of x? Should we have integral of something dy or the integral of something dx? This one's going to be dy because then you're only looking at one function. Okay? This one would be dy. If instead I wanted this, that would be dx. Okay? You could do both in this case. Let's say I want this region. What do you say? dy or dx? If I do dx, I'm slicing it this way, right? Well, when I go to slice this, I got an issue here. Right? I don't know. Dy, I don't have any issues. Okay? So that's that.